Hey everybody, this is example number 4 for structural dynamics of damp-free vibrations. So the problem statement that we have is for a viscously damp system, the free vibration trace measurements show a 60% reduction in vibration amplitude after 15 cycles, and the critical damping constant C sub C for the system is 50 Newton seconds per meter, and we need to find the damping factor and the damping coefficient for the system. So here's a representation in the figure below that we see of the displacement of the system. So what we're saying is that if we call the displacement here, the vibration amplitude here xi, and then one cycle is from this peak to the next peak. That's one cycle. We're saying after 15 cycles, so xi plus 15, we're saying that this is equal to we're saying that this is equal to, let me write it another way, 1 minus 0.6 times xi. So that 0.6 is our 60% reduction. So that equals 0.4 times xi. And we need to find the damping factor and the damping coefficient for this system. Before we proceed to the solution, I just want to let you guys know that this example is brought to you by Bentley. And Bentley Systems is a software development company that supports the professional needs of engineers, designers, planners, and contractors responsible for creating and managing infrastructure. Bentley has tailored software applications for design, modeling, and analysis of buildings, structures, bridges, plants, and more. I have used Bentley's software, and I can say that the software was very easy to use and the support that came with it was impeccable. Whenever I needed help, the Bentley team was there for me. Here is their website, it's bentley.com. There's a link to bentley.com and some of their YouTube channels within the description part of this video. So if you're a student and want to get familiar with the software and get a leg up over your colleagues during your job search, academic licensing is available through Bentley. And if you're a practicing engineer and you want to sharpen up your skills, they have a bunch of videos and webinars on their website as well as their various YouTube channels, so please check them out. And now coming back to our damped free vibration problem. So the first equation we're going to use is this relationship. It's n times delta equals a natural log of the ratio of the vibration amplitudes. So n is the number of cycles, delta is a logarithmic decrement, and then the equals the natural log of xi divided by xi plus n. So we simplify this a little bit more. So it's natural log of xi divided by, and as I mentioned, as I worked out the relationship, xi plus n is equal to 0.4 times xi. So that comes out to be the natural log of 2.5, which is equal to 0.916. So n times delta equals 0.916. And so based on this, we can calculate the logarithmic decrement. We just divide both sides by n, the number of cycles. So delta equals 0.916 divided by n, so divided by 15 cycles. And so our logarithmic decrement equals 0.061. Now we can calculate the damping factor zeta, and that's equal to delta divided by the square root of 2 pi squared plus 2 pi squared plus delta squared. So that zeta is equal to, our damping factor is equal to 0.0097, and this is less than 1, so this tells us that the system is underdamped. And now lastly, we can calculate the damping coefficient, and the damping coefficient, the relationship is that zeta equals C divided by C sub C. So zeta equals the damping coefficient divided by the critical damping constant. So we rearrange this equation. So the damping coefficient equals zeta times the critical damping constant. And we just calculated zeta, and we know from the problem statement that the critical damping constant is equal to 50. So our damping coefficient is equal to 0.486 newtons second per meter. And this is the end of this example. Please subscribe to the channel, like the Facebook page. It's facebook.com/engineeringexamples. And please also visit the website. It's EngineeringExamples.net. See you guys in the next video. Thanks.